On the 17th of August, an incredibly exciting observation for astronomy happened. The first neutron-star collision recorded from gravitational waves. We knew that neutron stars could collide in theory, but we've never seen it happen. This was only made possible by the gravitational wave detector that made headlines last year, proving the existence of gravitational waves. Ripples in space-time, travelling outwards from a source caused by some of the most violent processes in the universe, such as neutron star collisions. Astronomers were able to study this neutron star collision using more than just gravitational waves. They also observed it with different kinds of telescopes all over the world. Neutron stars are leftover cores from big stars that have exploded. They've gone supernova. If these cores are just the right size, say 1.1 and 1.6 times the mass of the Sun, as they were in this case, then they get squeezed down by gravity until electrons merge with protons to form neutrons and neutrinos, and the neutrinos take off, leaving the neutrons in a really densely packed star. A piece of neutron star the size of a sugar cube will weigh as much as Mount Everest. That's how dense they are. I spoke to Ed Dorr, a physicist at the University of Sheffield, to find out more. Here, Ed Dorr explains why neutron stars collide.
They collide because they started out quite close together. So you end up with a system where these two things are orbiting around each other. Because both of the masses are accelerating, they radiate energy. And that radiation takes the form of gravitational waves, which are basically They induce ripples in space-time, and those ripples in space-time carry energy away from the system. And because energy is going out of the system, if you think about, imagine you're rotating with the neutron stars, if energy disappears, then the two objects have to get closer together because of conservation of energy. And as they get closer together, because of angular momentum conservation, they spin around each other more rapidly. And eventually they're orbiting around each other for a short time at a rate of about 100 cycles a second. And then at some point there's no stable orbit that these two things can be in and still remain separate, and so they fuse together in a sort of cataclysmic collision. And at the end of the day, what you end up with is either one big neutron star, or quite likely you end up with a black hole.
The discovery of the first neutron star collision all began on August the 17th at 8:41 a.m. Eastern Time, when LIGO's interferometers detected a clear gravitational wave signal lasting 100 seconds. What was exciting was this was the first time we detected gravitational waves from something other than black holes merging, something we could see with telescopes too. By searching with telescopes, astronomers could pinpoint exactly which galaxy the waves were coming from. NGC 4993, about 130 million light-years away. That meant we could get our first close-up look at the explosion of radioactive material produced from a neutron star collision, what's known as a kilonova. And there was a lot to see. The kilonova put out everything from X-rays to visible light to radio waves. 1.7 seconds after the initial detection of gravitational waves, NASA's Fermi Gamma Ray Telescope detected a gamma ray burst brighter than 1,000 suns. Scientists have thought that gamma ray bursts came from neutron star collisions for decades, but the evidence has been lacking up until now. In fact, new observations with light telescopes have also shown that heavy elements like gold, lead and platinum were made in this event, and that helps us understand where a lot of the heavy elements in our universe come from. This one collision could have produced up to 100 times the Earth's mass in gold, so that's another great mystery solved. Ed Dorr explains what this discovery actually means for science.
Well, it opens a new field. So the analogy I like is Galileo's telescope. Galileo had the idea of using a telescope to look at the sky, and he looked through it, and the world changed forever. The impact of the gravitational wave detector is to give us a new way of probing the universe in a non-luminous carrier of information, something that isn't a photon, which is probably going to help us over a few decades, I suspect, gradually unravel the mass content of the universe.
This was our first chance to prove a lot of stuff that physicists had theorized for decades. Gravitational waves, kilonovas, the creation of heavy elements and gamma ray bursts. As we get our new gravitational wave detectors up and running, astronomers expect to see plenty more of these collisions, along with other types of gravitational waves, just in the next few years. It's phenomenal time to be studying the universe, and we're going to be learning a lot more about it pretty soon.